too many months ago, I collaborated with Chris and Jesse from the PlanetGeo podcast with 2 very long videos in which we discussed the oldest rocks on Earth, like the Acosta gneiss, Jack Hill zircons, and other formation names I cannot pronounce, how we date these old rocks, how the moon-forming impact reset rocks on Earth, how because of this impact we have to use non-Earth rocks like meteorites to date Earth, and a little bit about early plate tectonics and life on Earth. And at the end of our second video, I asked you guys to give me your follow-up questions so we could make another video answering all of your questions, and boy, did you. In fact, you guys gave us so many good questions that we're making 2 follow-ups. In this part 1, we will answer all of your questions related to radiometric dating of meteorites, the age of Earth, whether any rocks are older than Earth or our solar system that we know of, early plate tectonics, how pre-plate tectonic Earth might have operated, and how and when the first continental and oceanic crust formed on Earth. And in part 2, we'll answer all of your questions related to the moon-forming impact, whether that impact played a role in early tectonics on Earth, whether that affected early oceans or early life on Earth, and whether life and or the Great Oxidation Event, the GOE, played a role in affecting early plate tectonics. So with that, we'll jump right into the part 1 questions with Jesse. So getting right into all the viewer questions, which sifted through like 800 of these comments, guys.
That is so many comments. That's impressive. I'm amazed.
Again, it was really high engagement videos. Yeah. I think these discussions were really interesting to a lot of people, and obviously to us, because we went on for I don't know how many hours, and probably will again today.
Yeah, absolutely. And had to cut ourselves off.
Yeah, so one of the main things we talked about was the cool fact that we don't actually date Earth with Earth rocks, we date Earth with meteorites. So a lot of people were wondering, wouldn't the radiometric age of meteorites be affected by the heat and pressure of impact?
Yes, this is such a good question. So for meteorites, yes, absolutely. And for actually the rocks that the meteorite hits during an impact. And so it's kind of a question of scale. So think of what you're measuring, whether it's a rock or a mineral or a bunch of minerals or a bunch of rocks, and think about the sort of intro to chemistry. Is this a closed system or an open system? And so if what you're measuring, if you're taking one mineral grain and your data point is measuring that one mineral grain, then yeah, elements could have left that mineral grain or been reset in exchange with the mineral grain right next to it maybe during that impact process. That's the case with zircons sometimes. That's the case with a lot of other minerals. They react individually. But if you dissolve the whole rock, if you take the whole rock, crush it up, dissolve it, samarium and neodymium might not have moved far enough. They might have moved between the mineral grains, but the entire rock system has remained a closed system, in which case, if you dissolved your whole rock, that's a good data point still. So it kind of depends on the scale of your measurement and how much these elements, because we're really dealing with individual elements in these radioactive systems, how much they've moved. So it also depends on the type of system. So samarium and neodymium, those elements don't move in water very easily. They do a little bit, but not a lot. Whereas rubidium moves a ton. And so the rubidium-strontium system could be reset very easily, whereas samarium-neodymium system might not be reset. And so by kind of comparing and contrasting the different systems, you can work out what has moved and what hasn't. So that's what people do with, for instance, like lunar rocks or meteorites, is take one sample, whether it's rock or mineral, and make multiple measurements of that using different systems. So does the rubidium-strontium system agree with the samarium-neodymium system? Does that agree with the uranium-lead system? If they all agree, great. That gives us confidence it's not reset. If they don't agree, then maybe rubidium-strontium is actually recording the resetting age and things like that. So it's my instinctual reaction to that. But I mean, what is your take on this question?
No, based on our last conversation, what I've taken about geologic dating is that it's this like multi-proxy approach, just like with my research where I was trying to reconstruct past climates. Like we use multiple elemental systems, isotopic systems, and we know how each one behaves and what each one reconstructs and how each one is altered over time by different processes. And some are more robust under these alteration processes, and some are more robust under different alteration processes. So then we can utilize all of them to kind of see if they're all telling us the same thing and like corroborate our findings that way. And I feel like it's very similar in geologic dating where like, maybe zircon and uranium lead dating is good for this type of rock that's been under this kind of stress. And then, other isotopic systems or other minerals or the entire rock bulk composition is better for this kind of dating, depending on what that rock has been through.
Yeah, that's right. And I think that that's a really good analogy because I think people often, and maybe part of this question is people think that affected or altered or, disturbed is a negative thing or throws uncertainty into our geochronology when actually the disturbance, it's actually really interesting to know the disturbance. So actually sometimes we would target a system we know is disturbed because we're trying to get the age of disturbance, which then can help inform
Right.
our other data that is less disturbed. So if we know the age of the shock metamorphism from a rubidium strontium isochron from the meteorite, that can give us more confidence in one of the more well-preserved isochrons like a samarium neodymium system or uranium lead system. So it's actually more tools in our toolkit rather than damaged. Like people think of it as like, oh, you broke your screwdriver because it doesn't work. When actually it's like, no, it's a
Right.
different kind of screwdriver actually now.
Yeah.
And so it's another tool instead of a broken tool, I guess.
Yeah. Yeah, I feel
Anyway,
like a lot of times too, people conflate. I mean, everybody hears carbon dating or like, and we talked about
God.
this
Oh
in the
yeah,
last, we talked about this already, but everybody thinks there's just one way we
yeah.
do this. And it's like, no, the reason it works so well is because we have
Oh,
all of these things, all
totally.
of these different isotope systems that we can use to make sure one isotope system makes sense with the other one.
That's exactly right. And actually, like the age of the meteorite, for instance, in meteorite literature, sometimes we'll be interested in when did the rock form, the meteorite rock form. We'd also be interested in when did it get disturbed in many instances. So did that meteorite floating around or was it part of, maybe it's a lunar meteorite, so it's part of the moon. And then, it got hit and ejected or it got altered in some way, shape, or form. Then when did it come to Earth? When did it land on Earth? Like all these things are interesting data points. And so we're actually, the ability to use disturbed, quote unquote, systems is actually really powerful for understanding these processes, understanding the solar system processes, I would say. So
That's really cool. I also fell under that, I guess, misconception as well of just thinking the more altered, the harder to date.
yeah.
And the, less you
Well,
can figure out about
that
the age and stuff.
yeah,
But
yeah. It is, there are many systems that are altered and they're just a mess and we actually can't extract more information. Like our research group is working on altered zircons a lot now. And there are some of these things that we just can't make heads or tails of the ages. Like it's just an altered mess. We can't make any sense out of the confusion. So yeah, I don't want to present it as like it's a perfect system. We always get age information. Sometimes we do not get age information after a bunch of work.
yes,
Yeah.
yes. Well, there's plenty of rocks to work with. So
Yeah, yeah,
that's good.
absolutely. Absolutely.
That brings me to another question that was very commonly asked in
Yeah.
our comments from the last couple videos. And that is we talked a lot about zircons and dating using zircons and specifically uranium lead
Yeah.
system to date the rocks, especially when it came to the oldest rocks on Earth, like Acosta ice, which
Yes, nicely
I got
done.
my piece. If anybody hasn't seen the videos we made, go watch the videos where
Nicely done.
he sent me this nice. But yeah, this is over four
I hope
billion
that
years old.
that's not just sitting, next to your garbage can. It's hopefully sitting
No,
somewhere
this is
very
next to
prestigious.
my head at night. This is on my bedside table. And I look at it every night. I'm like, oh, so old. And I'm going to Iceland next year to get
Oh,
my youngest rock so I can do
nice. Oh,
the oldest, the youngest.
very
So.
cool. Very cool. That's awesome.
But even though this is super old, we know the oldest ones are the meteorites.
Yeah.
So we talked about how we use zircons for these old Earth rocks, but do we also use them for meteorites?
Yes, in certain instances. Zircon's not common in meteorites, not super common in meteorites. And you got to think of
Okay.
like what types of rocks meteorites come from. So we have rocks from Mars, meteorites from Mars. Those have zircons in them, and they're actually some of the oldest zircons that have ever been measured. They're 4.45 billion year old zircons, and they're incredibly pristine. This uranium lead data from them is spectacular. It's actually concordant. I think we talked about that briefly, but it's like really, really good data. We have rocks from the moon that also have zircons in them. Those are often shocked and have had all this whole impact history, but they're really useful as well. There are some zircons in other classes of meteorites, although they're pretty uncommon. And the reason is that most of the meteorites we have are either basalt, which basalt just compositionally does not crystallize zircon primarily, or they're iron meteorites or some combination of those two. Iron meteorites from like the core of a planetesimal, and that will not have zircon crystallizing in it either. It just has a stable mineral phase. So the answer is yes, we do, and some of the oldest zircons we've ever measured as a species come from meteorites, but they're not common because the composition of meteorites often reflect a undifferentiated or an undistilled planetary body. So
Yeah.
The ones who come from more distilled bodies like Mars and the moon have some zircon.
Yeah, well,
Certainly not as many as Earth.
I remember, yeah. And I remember us talking last time about, how as Earth differentiated, the zircons would typically concentrate in the more silicious, more fractionated, differentiated material. And so it makes sense
Yeah.
that really primitive, non-differentiated meteorites are not going to have a lot of zircons. So,
Yeah, right.
yeah.
Exactly. And this is a nice question that builds on the previous one about alteration, is that, one of the big outstanding questions in planetary, well, one of the many in planetary science is what is the impact history on the moon? Because the impact history of the moon is used to kind of calibrate the entire impact history of the solar system, the inner solar system. So knowing when craters formed, what the ages of the big craters are is a big question, because the moon is the one planetary body that we can look at, count the craters, figure out the relative order of all the craters, and then we have some chance of getting the ages of those craters, the real ages of those craters. So then we could plot the impact rate versus time of the solar system. And so one thing people do is they look at altered zircon from the moon, because the alteration is often an impact dating event. The
Right.
zircon is altered by, so that's one way where people kind of look for that. And there's some clear like textural things people can look at in zircon that say this is a shocked zircon. This thing got hit by a meteorite. Maybe not the zircon, but the shock wave from a meteorite impact passed through this zircon grain. Actually, one of the best acronyms, it's called friggin. Friggin zircon.
Oh my God. I just saw a whole talk about this at GSA or somewhere. Yeah.
Oh, yeah. Yeah. It's
I love
former reedite in granoblastic zircon. It's great. Friggin.
Oh, it was one of your
just
students.
awesome.
That's why. Yeah.
One of my students found a paper that outlined what friggin zircon was. I love it. It's such a good acronym. It's one of the few
acronym.
like the seismology community is great at acronyms. The volcanology community is awesome at acronyms. This is one of the best like petrology acronyms I've ever seen. So
yeah, geology acronyms are pretty good. There's some really fun ones out there.
Yeah,
That's
definitely.
amazing. Okay, so we will definitely get way more into moon stuff in the next follow-up video. But for the kind of follow-up to this question on zircons and if we use them in meteorites is, we talked last time about how useful zircons are. So a lot of people were wondering why exactly are zircons like the top of the top of dating material? Like, why do we use them so much, and why are they so great for that?
It's sort of like the perfect mineral for the perfect decay system. So we have all these decay systems, these geochronology decay systems. Rubidium decays to strontium, or one isotope of rubidium decays to one isotope of strontium. One isotope of samarium decays to one isotope of neodymium. Uranium and lead have a paired system. So 235 uranium decays to 207 lead. 238 uranium decays to 206 lead. And so that means we can measure one measurement of uranium and lead in a mineral grain or a rock gives us two ages that we can compare and contrast with one another. So they're kind of like two different sundials that you flip over and they run at different rates. And if you know the rate, you can compare how well the sundial is looking. So we can kind of intercalibrate the two. And zircon is an amazing mineral for this because it takes in uranium when it grows from a magma, but it excludes lead. Lead is a huge ion with the wrong charge to fit into the zircon structure. And so it'll take in uranium, excludes lead, gets us mostly away from the initial daughter problem with isotope geochemistry, but it also is really robust to later alteration or later disturbance, later metamorphism. It'll survive in a weathering cycle. It'll survive most metamorphism. And so it's really great for that. There is a small but growing interest in zircon alteration events. So it is a weird mineral because it's really resistant. So you can imagine the crystal lattice is really rigid. It's like a steel building with all the I-beams going everywhere. It's really rigid, but the radioactive decay blasts apart little parts of that structure. And it's a very rigid crystal lattice, so it doesn't sort of self-anneal. It doesn't heal itself very well, which other minerals sometimes do. And that's great for preserving the initial age, but it means that at low temperatures, fluids can sometimes get in that radiation damaged bits and remove lead and disturb the system. But again, back to our earlier conversation, the disturbance is interesting. And the fact that it is disturbed, we can often extract age information from that. So that's why things like zircon might be really good at recording the shock event, the deformation alteration event on the moon, in addition to the crystallization age.
Oh, wow. Yeah, zircons, they're pretty cool. Well, I think it's really cool too
neat, huh?
that I think it's awesome that they're like this thing that survives all of this, later metamorphism, but within like a matrix that, of other
Yeah,
minerals that might show those later events so that you can get this entire history of the
totally.
rock
Yeah.
where the zircons give you the oldest history and then you see the rest of all the events and the other minerals and other isotope systems. So I just think
Yeah,
that's really cool.
absolutely. It's you can piece together in that rock you're holding in your hand. People have, I mean, it's one of the more famous old rocks, and people have looked at basically all the mineral grains in that rock for geochronology, so you can piece together like a really amazing story. The sort of full life events of that rock are pretty recorded, and zircon
Yeah.
starting out, and then all the
Well, I
younger ones too.
remember you talking about like there was a metamorphic event at 1.8 billion
Yeah,
years ago, and then 1.3, and then 1. And it's like, how do
yeah.
we know all this? It's
How
just
do we know all
so
this stuff? It's
amazing.
amazing.
Oh my
Yeah,
gosh.
yeah, yeah. Lots of work, lots of PhD theses working on it. This is particular suite of rocks.
Yes.
Lots of effort. Yeah.
Well, and speaking of kind of our precision now with geologic dating, a lot of people were really shocked at the precision of this number that you mentioned in our previous videos, which is that we think the Earth is about 4.5682 billion years
Oh
old.
yeah.
So the Earth and the solar system based
Yeah.
on like our meteorite dates, which is like so 4.5682. I mean, that seems like so, just precise. And so a lot of people are wondering, what is that actually dating? Like what defines
Oh.
the birth of
Oh.
Earth, which I think was
What a.
I mean, this is almost, we're getting to like the philosophical range of things again.
Yeah.
But
Yeah.
yeah,
Yeah. Yeah.
what defines the birth of Earth? And also another person asked, what does this number actually mean? Does it mean when Earth reached a certain size or when Earth's
Right.
crust solidified or something else?
Okay. That is such a great question. I mean, and Chris and I, we have a whole podcast episode basically about this question, about this exact
Really?
thing. Like, what does that number mean? Because it was something that Chris in his astronomy class had students had come with a question about, what is the age of the Earth? What does it mean? What does the age of the solar system mean? Is that the same as the Earth? Is it different than the Earth? Like, how does this work? Short answer is that age, 4.5682 billion years, or 4568.2 million, is the age of the condensation of the first solids of our solar system. So the first things that kind of condensed from our early solar system disk, that's time zero. So we kind of say that number, 4.5682 billion years ago, is the start of solids in the solar system. It's not the age of the Earth, because we have to, in order to build a planet, we have to take all this gas and dust and aggregate it together.
So, well, okay, before you go any further, what
Yeah,
exactly solid? Okay, but like
solid.
like does dust count?
Well, dust is yes, but not in the way, it's hard to date that stuff.
Okay.
And there is some dust that's from before the solar system as well that we can find. But these are what are called CAIs, calcium aluminum rich inclusions. So there's some petrology that just goes into these things, but it's kind of gas and dust accreting in this really hot disk of stuff. And so they're getting together and it's being kind of melted together and then forms this little inclusion. So we find these as inclusions in primitive meteorites.
So
There
those
are
inclusions are what give us that 5 point, what is it?
4.568.
4
Yeah,
point, yeah.
exactly. Yep. And these are like uranium lead ages in those systems,
Okay.
in those particular meteorites. So
Yeah.
that kind of sets time zero, and then from there we work forward. And basically, the first few million years are formation of chondrules. Some people might have heard of chondritic meteorites. These are things that have chondrules in them that give ages that are like 4.565 instead of 4.568. So a few million years, things are starting to coalesce. But forming a planet is a totally different ballgame. Like small dust runs into dust and it makes bigger stuff, and then bigger stuff has more gravity, and so it attracts all the other stuff, and so this kind of starts to grow as a positive feedback loop there. And these planets are getting hot. There's all sorts of radioactive elements around. So they're heating up, they're internally melting, and the big ones get bigger because they start to attract other stuff. And that process, well, I don't know. When is a planet a planet? Like, what is the event? Is there a single event that like marks that in time?
I don't know. I mean, I like the idea, like the one person that said, is it when it reaches a certain size, but also at the
Yeah.
same time, I mean, we have planets of very, very different sizes. So I
Yeah,
don't know what that
definitely.
would be. Yeah, I don't know enough about the early solar
Yeah.
system because then you got asteroids versus planets and like how they all
Right.
start to
Yeah.
like
Yeah, for sure.
orbit. I don't know.
It's a tough one, and I think there's no to me, people focus on what they can date rather than any genetic definition for what a planet is, like
Right.
I don't know, any size. So we focus on stuff we can date.
Yeah.
And one thing we can date broadly is when the core formed. So when the
Oh,
planets are getting hot, so even small planets at that time will have gotten pretty hot because there's a bunch of elements around that are rapidly decaying away, generating a ton of heat. Aluminum has an isotope that was decaying away like crazy. And so it'll heat up and it'll melt, and as soon as some planetesimal melts, then the heavy stuff can drop to the bottom. Think of it that way. The core, the iron core, will form. And so we can date that process on planetary bodies. So on Mars, it's, kind of around 10 million years when the core formed, or when the planet was mostly accreted. And we can use a short-lived system called the hafnium tungsten system to date that. Anyway, so that's the kind of time frame for forming a planet, sort of tens of millions of years for getting these planets kind of formed. And then there's a whole bunch of physicists who do the simulations. They kind of simulate solar system formation, and they can kind of see this physically.
right, right.
Then we have a planet that has a molten core, iron nickel core, and then silicate stuff above it. But that silicate stuff is almost certainly molten for a while. And so we have what's called a magma ocean planet now, where the mantle's not solid, the mantle's all liquid. And there's probably some like crust on the surface, some, thin rind of stuff that's crystallized. And then the question is, when does that mantle crystallize, fully crystallize, or separate out into chemical parts? And that's a whole other question, but that's like maybe a 50 million year to 100 million year kind of process there.
Yeah, no, that is a good way to explain that kind of the time zero thing. But yeah, I feel like I never thought too deeply about like what defines the birth of Earth. I mean, I always just
Right.
took our like 4.5682 billion year ago time point as like the beginning of when planets
Yeah.
started to form, and then every planet obviously took its time doing that. But
Yeah.
yeah, that's
There's
such a
so there's a great paper, one of the early papers in geochronology. It's from 1956 by a guy called Claire Patterson. And the title is just Age of the Earth. And it's an amazing kind of first look at uranium-lead isotope systems from a whole bunch of different rocks, ore deposits, clay, these weird iron nodules, and basically created what's called a planetary isochron for it. So the age of the entire planet, from looking at all the different chemical rocks on the planet, comes up with an age broadly of 4.55 billion years ago, which
wow.
is amazing to think about, because I just described an evolution from like 4.568 and then 10 million, maybe 50 million years later, and that's the number.
That
Like
is,
it's the same number with less precision. So not much has changed since the 50s or 60s. I mean, we've gotten a lot more detailed, a lot more.
You have a lot
higher
more data, but
resolution,
the fact that it corroborates that still is pretty cool.
exactly from
Yeah.
that work, it's just like such a cool, transformative initial data set. It's amazing, amazing.
Oh my God, amazing. And yes, in the next video, we will talk about the moon forming impact and how that reset things. But the next
Yeah.
question for this one, and you hit on this a little bit in your answer to that one, but have we ever dated rocks older than our solar system? And if so, where did they come from and how do we
Yeah.
know?
Right. I would say, have we ever dated rocks older? No. We've dated fragments of things. And these are, and again, I'm not the expert on these. Pre-solar grains is what they're called. And the name tells you a lot. They're grains from before our solar system, pre-solar grains. They're crazy. Where I did my postdoc work at the Carnegie Institute of Washington, they have a bunch of people who are experts on these things and spent careers studying pre-solar grains. But they are a lot of silicon carbide. They're basically incredibly resistant dust, really resistant dust that's left behind in certain meteorites that have not been melted. And they're in primitive meteorites, so people can extract them by doing this like really aggressive acid leaching, and these things are what's left behind, basically. And we know that they're not from our solar system because they have incredibly crazy isotopic compositions. So just things that we do, they're orders of magnitude different in a bunch of isotopes than anything in our solar system. So they come from outside our solar system, and
Could we
hence
ever track
pre-solar grains.
what solar system did they come from? The solar system that was here before our
Yeah,
solar system? Like, how do we?
It's yeah, you're pushing my knowledge a little bit, Rachel.
We're getting into
What
philosophy.
what they do talk about is they talk about types of star systems.
Oh, yeah.
So is it a red giant, or I'm going to get this wrong. The astronomers will hate me. For
Right,
this,
right.
it-
But the
different
star types, yeah.
types of supernova, different classes of supernova generated these things, or parts of a stellar life cycle would generate this particular grain. so they kind of categorize them in different classes
Yeah.
without talking about, it came from the one just before us or something like that. Yeah.
Okay. Yeah, I do want to make the disclaimer that we are Geo Girl and Planet Geo, not Astro Girl and Planet Astro. So we,
That's
if we
right.
get any astronomy things wrong, don't come
Yeah.
at us. Just let us know
No,
in the
that's
comments very nicely.
Yeah. That's right. I just want to go look at rocks and
We are
granites. I'm
answering
not
your
worried
questions.
yeah, I'm not too worried about astronomy things. So yes, I like that.
I've had to say that
Planet astronomy.
before. I am Geo
Yeah.
Girl, guys. This is
Yeah.
Geo.
Emphasis on the geo.
Yes.
Stick to what
Okay.
you know. Yeah, I think that so these things they're really crazy. I remember I might get the details of the story wrong, but there was somebody who told me when I was working at Carnegie, they do this work in Antarctica a lot, and they can get these like big dust vacuums that are basically sucking dust out of the air, and the circulation on Earth says that most of the dust there, or some, not most, but much of the dust in this area will be from outside of the planet. It's not planetary dust. It's like coming in from space. It's a lot of space dust. So they suck these things in, put them through some filters. And we're talking about these pre-solar grains are like a micron. These are millionths of a meter across. They're tiny, tiny things. And then they'll look at the filters, and there'll be some larger fraction of pre-solar grains in there. And so these things in Antarctica and a lot of the Antarctic meteorite collections have pre-solar grains in them, but we've kind of reached my knowledge of them. But some of them are very old. The model ages for them can be like up to 2 or 3 billion years older than the solar system itself.
That is
So we're going back
nuts.
6 or 7 billion years. Yeah, it hurts to think about,
Wow.
to be honest with you.
Yeah, that is
So-
just, I thought that was a really, really intriguing question. I wish we knew
Yeah.
more about it, but yeah, the
Yeah,
answer is
totally.
yes. And we can tell because of isotopes, and that's all we got.
That's about it. Yeah,
That's all we
exactly
got.
Right. I think we can leave it
but
there. Yeah.
the rest of the questions are very much more geocentric.
Okay, perfect.
So now we gotta want to switch gears into early continents, cratons, and plate tectonics. A lot of the questions were about kind of the
okay.
beginning of plate tectonics and stuff. Very interesting stuff. So the first question, just to kind of kick us off, is what is the difference between, if there is, a craton and a continent?
Okay. So craton, that's a great question. Craton, think of cratons as the core, the thick cores, basically. They're usually ancient. So part of the definition, and these are both like sticky definitions or sort of squishy definitions maybe, but cratons are often stable for billions of years. So they often have a lot of old rocks on the surface. They also have really thick roots. So the lithosphere, if you think about what is a tectonic plate, what makes up a tectonic plate, it's the crust and the mantle lithosphere part beneath it. So the mantle that's kind of riding along with the crust, that's cool and rigid. Cratons often have very thick lithospheric roots. So more than 150 kilometers thick, maybe even down to 250, 300 in some instances. We call those things keels. Like think of a sailboat that has this keel going down that's kind of stabilizing the thing. Cratons are smaller than continents. Continents are made up of a bunch of cratons. And so continents, again, squishy definition, depends kind of what type of scientist you're talking to, but they're above sea level. They're seismically thick, so the crust is thicker. The crust is more like 30 kilometers thick, whereas oceanic crust is 7 kilometers thick. And it's usually more evolved, more felsic, more silica, more potassium, sodium, etc. It's not oceanic crust. The continental crust is
It's just
not
not.
oceanic
That's
crust,
a
right?
great
Basically.
definition.
Like,
Continents, what
So-
are they? They're not oceans.
they're not oceans.
Yes.
The other part of the bimodal curve. They're not the mode that is ocean. So
That's funny.
that's kind of the general definition. Cratons are really interesting because they're very important resources. They have most of the world's extracted gold and platinum are in cratons, and along the margins where the cratonic core is kind of remaining solid, but the margins between them gets deformed and has this history of deformation. That's where a lot of metal deposits end up occurring. So it's not just a sort of an arm-wavy ambiguous definition. Like the definition kind of matters a little bit here. So
Yeah. Yeah.
Anyway.
No, I love that. I read a thing that said cratons are like the continental seeds that continents grow around, which I think is
that's a good
pretty
one.
good. But you're
Yeah.
right. It depends on the scientist. Like continents, I mean, of course, they have a certain thickness. They're a different composition than oceanic crust. But then there's tons of places where they're a lot thinner or they're a lot
Yeah.
thicker or they're more basaltic, but they're still not oceanic crust. So then it's like, because there's so much
Yeah.
variation. But
Totally.
overall, they're the, thick, silicious, less dense stuff.
Oh, okay. Yeah, I like that. That's a very good. I like that. It's a good one. Yeah.
Okay, so we talked about last time how the continents came later, there was
Yeah.
oceanic crust or some kind of big mixture of like crust on Earth. And then continents differentiated out later. And we'll get into differentiation in the next question. So we don't need to go
Okay.
into that
All
right
right. Don't go
now.
there. All right. Fair enough.
But the first thing that people were wondering is what was the first continent and or craton? Like, was it I
Oh.
know there's hypothesized early supercontinents like
Hmm.
Valbara or Kenorland. I don't
Yeah. Yeah.
know
Yeah. Yeah.
how
So
confident we are around those or what our evidence is even.
yeah. Oh, that's a great question. So if we look at the rock record, the preserved rock record, like what are the ages of the rocks that we see on the ground today? We have less going back in time. So by like 2 billion years ago, the rocks that we see on Earth that are older than 2 billion years are tens of percents, a couple, 20%, 25% or something like that. So what that means is by about 2.5, 2.7 billion years, it means that there's less rocks, but there are still rocks there. So we can start to kind of do things, look at those 2.5 billion year old rock packages, 2.7 billion year old rock packages, and we can kind of compare and contrast them to each other. And people have done this, and there's kind of two camps. If you go back to that time period, 2.7 billion years ago, roughly, some people would argue the kind of classic argument is that it was all one supercontinent called Kenorland. That's kind of
Oh.
the big supercontinent model. The other model is that it wasn't one big supercontinent. They were disaggregated into maybe three. Then one's Valbara, one's Sclavia, one's Superia. Like that, they're different little microcontinents or aggregate cratons, where multiple cratons were together. And so, in those cratons, think of them as breaking and forming, breaking and going back together over time. And so, if you break the puzzle apart, put it back together, but you mix up the pieces, then you break it apart again, put it together, mix up the pieces, you can imagine stuff that used to be next to each other is now caught up in different continents. And so, that's kind of as far back as we can go with any degree of confidence. We get back 3.4 billion years ago, and like there are rock suites on Earth that are 3.4 billion years old, and some of them have some similarities to each other, but it's really hard to connect them together and say, was it one continent 3.4 billion years ago? How big was it? We have no idea. Were they all connected, or was it a bunch of different little disaggregate ones? Again, no idea. It's really hard to do that kind of work because the further back in time, the less rocks we have and the less diverse rocks we have. When we go back to 3.4 billion years ago, we're stuck with like metamorphic gneisses. That's pretty
Yeah.
much all we have. We don't have sediments. We don't have basalts. We have some, but not many.
Yeah.
So it's really hard to kind of link things up in that way.
Well,
Going back in
speaking
time.
of nices,
Oh, yeah.
sure.
Exactly.
I know we talked about in the last video about how the oldest rocks on Earth, things like Acosta gneiss, have zircon grains that suggest that their earliest formation was over 4 billion years ago, but that predates all of the earliest cratons and continents that we're talking about. So what exactly, because we know we talked about how zircons tend to form in more silicious material, more
Yeah.
continental crust-like material. So what are these earliest zircons telling us? That there was true continents back then, or was it
Yeah.
kind of like the earliest start of differentiation that these are dating?
The answer is we don't know. We really have no idea because we just have so few locations with zircons that old. There's a couple locations with
Yeah.
zircon grains that old. And we can look at the modern Earth and we can say we can form zircon bearing rocks in many different ways, right? Meteorites have
Yeah.
zircons. Mars has zircons. The moon has zircons. Iceland has zircons. Plate tectonic subduction zones have zircons. Continental collision zones have a lot of zircons. So zircon itself forms in more felsic, more silica-rich rocks, but it doesn't necessarily mean that we know the tectonics of that production.
Yeah.
And it depends on who you talk to and depends on which grains you're looking at. There's some fairly convincing data from detrital zircons in the Jack Hills that those were related to plate margin type sequences.
Wow.
In Acosta, I would argue that they're more like Iceland-like processes, not necessarily plate subduction
Right.
going on, but more like
Interesting.
what people call intracrustal working, or
Well-
kind of a thick plateau that's internally melting itself.
Right. Okay.
So,
Which
yeah.
is kind of more similar to the early tectonics that I've heard about. But when
Yeah.
you mentioned something like plate margin, it kind of
Oh, yeah.
suggests plate tectonics, which brings me
Yes.
to the next question.
Oh, okay. Yes. All right.
Because a lot of people were wondering. I mean, I know we talked about how the beginning of plate tectonics on Earth, global plate tectonics, is still very uncertain,
Yes.
the timing of that. But you mentioned Jack Hill zircons
Yeah.
in Australia are what, 4.4 billion years old or
Yeah,
something?
4.3, 4.35. Yep.
Yeah.
Yep.
So that's way before a lot of the estimates of when plate tectonics are proposed to have begun, like 2.5-ish
Yes.
billion years ago. So there were a lot of questions around like when did plate tectonics begin and what is some of our evidence. So I'm going to read off some of these
Okay.
just because I find their wording very intriguing.
The
And
questions,
also,
the questions
yes.
that you mean.
Yeah.
Okay.
So somebody asked, how did early continents form on a pre-plate tectonic Earth? One person said, how can people even doubt that there were plate tectonics if there was land or continental crust?
Ah,
And then I guess we had talked about subduction. So somebody said, you say that subduction drove crustal differentiation and thus continent formation, but subduction typically occurs when oceanic crust subducts beneath continental crust. So how did the first continents form? Was it subduction of oceanic crust under other oceanic crust? And lastly, would this have been classified as subduction, or would it have been more like drift tectonics, or some people have called it in the literature sagduction tectonics,
sagduction.
which I
Yes.
love.
Okay.
So all of these questions I think are getting at one, we kind of need to talk a little bit about differentiation before we kind of answer them. But they're getting at, yeah, when did plate tectonics begin, and how can we even say that continental crust was forming before that? So can you talk a little bit about, before we get into those, like, can you just tell us
where do you want to start there?
why are these questions even a thing? Like, why do we try and necessitate plate tectonics for continental crust formation? And I think that needs to be kind of a conversation around what is partial melting, what is differentiation, and how does silica-rich crust form?
Gotcha. Okay, so yeah, the first thing, distillation is a great word. I love that word. It's or differentiation, kind of the same thing. How do we get continents that are more rich in silica, potassium, sodium, etc., and are buoyant and are thicker? And on Earth, we can look around and say subduction zone is a good way to do that. A subduction zone system is kind of taking oceanic crust, it's shoving it down into the mantle. That oceanic crust dewaters, sponge that gets squeezed out, the water goes into the mantle, melts the mantle, and then that water-laden basaltic stuff sits there and fractionates and creates evolved stuff up at the top. So that's what happens on the modern Earth. It's a good way to do it. You can also do it by smashing continents together, and stuff that's caught up in the middle gets melted and internally differentiates itself. To create ultra distilled crust and therefore ultra stable crust, we often need really high temperatures in continental collision, and maybe even continental collision zones with sediments involved, because basically you need to smash stuff together, heat it up, and do partial melting, not full melting, but partial melting, which is distillation.
Yeah.
Did I answer? Is that
I think
enough to go into the questions, or?
Yeah, my like main thing with this, because this, when I learned about this, it like blew my mind. Because at the beginning of my geological journey, I was like, how did we get these two very different end member types of crust? How did we get these really buoyant silica-rich continental crust and this really dense basaltic oceanic crust? And how did that differentiate on early Earth and then start moving around like plates? And when I learned this, it like made everything so clear for me. But the point I want to drive home is when you said partial melting. Essentially, anytime, and correct me if I'm wrong, but anytime we have rocks in the lithosphere or, crust, or anytime in the interior of Earth, rocks melt, that melt is more felsic than the original, like what's melting, as long as it's partially melting and not all melting. So if you have this, set of basaltic rocks and you raise the temperature enough to melt some of it out, but not all of it, that melt, and then whatever re-solidifies from that, will be more felsic than the basalt you started with, because the felsic stuff melts first. And so everything in the crust, when we have these collisions and stuff in between these two plates starts to melt, not everything melts, just some of it. So everything is essentially at plate boundaries a partial melt, and whatever melt is melting is going to be more felsic. It's going to be more differentiated than the original material. So every single time on early Earth, when things started to, solidify, and then we had partial melts form, and then things ran into each other and partially melted that partially melted material, and then again and again and again, it became more and more silica rich every single time till we got continental crust, and then a bunch of continental pods smashed into each other to form these big continental land masses. And now we have these big, very end member two types of crust on Earth. And so that's kind of the way I think about it, is just this differentiation process started small and then built upon itself. But like you said, on modern Earth, the biggest kind of regional process of partial melting where this happens, where we have continental crust material forming, is at subduction zones, at plate boundaries that are going under continental crust and melting that already more felsic material. And that's key because that brings up the question of, if that's how it happens today, how did it happen before continents were a thing?
Yeah. No,
And
that's
before
right.
plate tectonics was a thing.
Before plate tectonics was the thing. Yeah, for sure. You're right that there's multiple processes that can generate the same type of rock. Like we can generate a granodiorite in a bunch of different ways on the modern Earth. So the rock type itself is not necessarily indicative of a tectonic regime or a tectonic process. On the modern Earth, we generate a lot of andesite and granodiorite at subduction zones. And subduction zones are great because it's a conveyor belt of stuff. Like it's bringing water down in the mantle's recycling, it's melting over and over and over and over and over. So we can do huge volumes that way. It's a really good way to grow continents by doing that process.
Yeah.
So on to the continental or the plate tectonics question is such a sticky one. There is a bit of I wouldn't say consensus, but like a majority view that plate tectonics as we know it today kind of started around 2.5 or 3 billion years ago. I don't buy that. I'm not a believer in that.
Okay.
I think that's not accurate. I think there's
When do you think it was?
I think it's earlier. I think, and the way one of my colleagues, I think, does a nice way of framing it. It's not plate tectonics or non-plate tectonics. He breaks it up into mobile lid, meaning the lithosphere, the rigid outer part of the planet, is breaking, and stuff on the surface is making its way down into Earth. That's a mobile lid.
Okay.
And then he puts it in the stagnant lid regime, where the lid is not breaking. Like Mars is a stagnant lid planet. There's one tectonic plate. It's not breaking and diving down into the mantle in any way, shape, or form. And that kind of gets you away from what is the driving force of plate tectonics and what is a subduction zone. You can kind of that's like a higher level categorization.
Yeah.
And so my view is that something mobile lid tectonics, I think we have some evidence for it happening back to 3.8 billion years in certain locations.
Yeah.
And then, something similar, a mobile lid regime of some kind was operating since that time and just progressively growing continents.
Yes.
But
I think you're right. It's kind of like what defines the birth of Earth. I think are we talking one subduction zone on Earth? Or are we talking globally operating mobile lid plate tectonics? That's, I think, two different time points that probably took millions, if not billions of years.
That's a really good point. And I think what something seems kind of a thing that comes out of the modelers, the people who try and model these processes, is that if you go back in time, you heat up the mantle. So you go back in time, the mantle's almost certainly some bit hotter. And so what happens, it's harder to get a long-lived, like hundreds of millions of years, subduction zone system that's kind of a plate diving down as a rigid block. What seems more likely to happen is as the mantle heats up, that rigid plate that's diving down heats up quicker, and therefore it can break. So it kind of gets squishy and breaks off, which kind of locks up the subduction zone. So we kind of get this stop, start sort of subduction zone system, which is mobile lid, but it's certainly not plate tectonics as we know it today. It's not like modern styles of plate tectonics. So it's more local, short-lived, punctuated tectonics maybe, or punctuated plate tectonics. So
well, I think that's also similar, I think, to like the sagduction, or maybe a transition from sagduction, which I think was more just like things dripping down rather than subducting down. I had Steve Bauman on to talk about this, who has a channel. It's great, so go check him out, or go check out, I'll link that video down below for you guys. But he kind of explained it as it was a more vertical process as opposed to a laterally moving plate process. So today things are moving laterally, plates go down and they, sometimes subduct pretty shallowly, but then as things were hotter in the mantle, it would just kind of sink down and drip and then melt and then recycle. So I think it was a lot more, things like hot spot plumes and then dripping down and sagduction in the dense areas. And that led to, these partial melts and the beginnings of differentiation when it wasn't a full blown plate boundary. But that's why I found your description of the Jack Hill zircons as, potentially being indicative more of a kind of plate margin type
Yeah.
tectonics very interesting. And it makes sense why now, you say that your stance is that plate tectonics started earlier because of things
Yeah,
like that.
these are really complicated geochemical arguments that are probably not worth going into because it's suffice to say there's debate about what they mean. But the subduction, I kind of break the mobile lid regime, horizontal mobile lid tectonics of some way where the lid's breaking and you're kind of thrusting stuff underneath of other stuff is a really good way to do a lot of partial melting because you're taking water or hydrated stuff at the
Right.
surface and shoving it down, and water is just a lubricant for melting.
Yeah.
And so water will induce a lot more melting. The problem that I have with the vertical tectonic arguments, the sagduction, the kind of drip tectonics, heat pipe volcanism, is that you're starting with dry stuff and you're moving that dry stuff up, and it's pretty hard to get wet stuff, hydrated rocks and water down deeper.
Yeah.
It's hard to do a lot of melting in a vertical kind of process, a vertical tectonic system in some way, shape, or form. So, you'll talk to 10 other people and you get 8 other opinions about
I
this.
know.
That have
Well,
very
again,
different
like you
opinions.
said, the further we go back, the less we know, but it makes it super
Yeah.
exciting. The other
Yeah,
thing, or the other part of that question I want to answer or try to attempt an answer at is,
sure.
so we mentioned how, subduction of oceanic plates under continental plates is a really great process for getting partial melt after partial melt and really, really felsic material. But we had the question of like, how did this happen before continents? Like, what was the first subduction zone if oceanic plates subduct under continents? And the short answer is yes, oceanic plates can subduct under other oceanic plates because oceanic plates aren't all the same exact density. And sometimes you do have that happen, even on modern Earth. But that is, to my understanding, kind of how everything began. Maybe not in a full plate subduction mode of tectonics, but different densities of this heterogeneous mixture of oceanic crust started to cause the downward movement and the upward movement of different types of rocks until you had, and even we see even today, like it obviously didn't have to start with like full-blown felsic material because even these zircons that, like we said, we can find these at places like Iceland where it is basaltic, it is not felsic, it is mafic. So like oceanic crust, can create zircons. But yeah, it's my understanding that it would have started with essentially very slight changes in oceanic crust density to this ocean. I don't know.
It's a tough. So you're highlighting one of the difficulties here is that we don't really understand at a great deal of detail how you break a lithosphere. How do you create that initial break? I mean, it's a lithosphere. It's strong. It is lithosphere because it's cool and strong and solid. How do you break that initially? And so there are groups of scientists who publish a lot on meteorite impacts being a big meteorite impact could break the lithosphere, and you could maybe start a subduction zone system that way. I'm, again, a little suspicious of those arguments, I would say, as being a major player. I just don't think we see much evidence for that. But it points to it points to the problem is once you break the lithosphere, once there's a break and you have a weakness there, it's easy to reactivate that weakness. We see this as faulting all the time. A reverse fault will turn into a normal fault.
Yeah.
And the same fault will be active multiple times in over millions of years, hundreds of millions of years. And it's the same thing with a break in the lithosphere. But how do you start that process is a tough one. And so I think it's a tough, you're pointing to exactly like the tough geodynamic problem of how do you create that initial break? You probably have to have some density difference, some age difference, some little bit more felsic block over here. I kind of like the Iceland analogy, and there's some modeling from the 80s that sort of went back and said, okay, that if you create this little felsic proto-continent thing, that could be an initiation point for breaking the lithosphere and creating a subduction zone that then like maybe it shuts off,
Spreads.
but then it has a fault in there, a break in the lithosphere that could be activated again over time.
I wonder,
It's tough.
isn't that kind of how like hotspots today can lead to these, kind of Y sections or triple junctions of like faults that go off. And then that can eventually lead to this just full blown divergent plate boundary, right? I mean, we have these rift zones that start from like a hotspot splitting apart the continent, and then that forms like I learned this process a long time ago. I don't remember. Do you know what I'm saying?
No, I know. But it's also how do you break a supercontinent apart? The geodynamics that are kind of tough. Maybe the mantle just gets so hot under there.
Yeah.
It's like an insulating blanket that then has to punch out.
Yeah.
The other thing that we have to think about here is that the continents are distilled. which means that we have to have some. You talked about the partial melting, you described that really well. What happens to the stuff that's left behind? We have to think about that. That has to go back into the mantle probably. And so that means that lithosphere, and we've seen this on actually the east coast of North America, there's a big 150 by 100 kilometer block of lithosphere that's been removed. That's not there anymore. It probably is related to some of the little volcanic plugs in Virginia that we see. But the lithosphere has dropped off into the mantle. And that's a good way to start to break a continent, right? There's a weakness now there. And if you push heat up into there and create melting and start to create a fracture system, that's one potential way to kind of break a continent apart. And then there's plate forces, subduction zone systems and the Wilson cycle, the classic Wilson cycle argument.
I mean, that's the thing is like today's system is just so different because when you look at a modern system where, yes, you can have a hotspot type, volcanic plume cause this breakup of a continent and eventually turn into a divergent boundary that's laterally continuous, but that is also driven on either end by subduction zone processes and slab pull. And
slab pull. Yeah, slab pull's the whole game, and the slab pull is probably tough to do on the early Earth.
Yeah, exactly. You don't have that.
Because the slab's breaking off.
So would that have turned into kind of this laterally continuous plate boundary on early Earth? I don't know. Maybe not. I don't know. That, I think, out of the entire, like, going from heat pipe volcanism, like, kind of like Io type volcanism to mobolid to this, like, melty vertical drip tectonic regime, subduction regime, to then mobolid plate tectonics, to then finally stagnant lid once Earth cools off. The series of events makes sense when you think that Earth started really hot and it's been cooling this entire time. The lithosphere is getting thicker. That's why we're seeing these changes to the tectonic regime becoming more rigid and hard and cold. But that transition between the drippy to the platey, the horizontal, the vertical to the horizontal is the one that makes my brain like so confused. And it's also that we don't have any modern examples elsewhere in our solar system. Like Mars probably once had plate tectonic. There are other, Venus might have plate, I don't know. But like,
debate.
They don't now.
Yeah, for sure.
We don't know.
I think that's a really valuable point is that plate tectonics is rare when we look around our solar system. And so going back, we know, almost certainly after the moon forming impact, there wasn't plate tectonics happening right then. So, but when does our mental model switch from being like plate tectonics is the default or is not the default to plate tectonics becomes the default? Because we go back 100 million years ago, plate tectonics was probably happening. So but at some point in that time, we have to flip our mindset from like plate tectonics was probably happening, or is the null hypothesis to be disproven to plate tectonics was probably not happening. And so, we have to prove that it existed. So it's a really tough question. It's a really tough question. We have no data. And we've been debating this as a scientific community for decades and decades now. And,
I think the primary answer to a lot of these questions is we don't know fully. So.
We don't know. That's right. That's exactly right.
Suki's coming in to say enough on that question already. Let's move on.
I'm sick of this question, Suki. Me too.
I'm so done with this. It's been forever, and all you guys are saying is that we don't know.
We don't know. Yeah, exactly.
But the next question I really like, because this one is also one I think that had me confused as a geology student for the longest time. But essentially it is, if continental crust today on modern Earth is not being produced at mid-ocean ridges, it's not recycled at subduction zones like oceanic crust is. Oceanic crust is being produced, it's being recycled, it's got this whole cycle, it makes sense. But continental crust is kind of just sitting there. It's riding above the oceanic crust that gets subducted underneath it. So does this mean that continents formed early on in these differentiation processes that we're talking about, and then all the felsic material came out of whatever early crust it was, and that's all tied up in continents now? Like, has Earth finished differentiating, and is this all the continental crust that Earth can form, and is it no longer forming, or is it still forming? I don't know.
Oh my goodness, this is such a great question, and I have thoughts but no answers. There's some answers. So on the question of are we forming more continental crust, it's a really good, really open question, because we don't know how much, if any, continental crust is getting recycled into the mantle at the moment. Okay. So we know we're like getting more attached, subduction zones, like accretion of arcs.
Accretion, right? Yeah.
Right, like There's an arc, the coastal arc batholith in India that, got caught up in the collision, was part of the mantle pretty recently, now is part of the continent. We know that that's happening. We don't know how much is being recycled into the mantle. So how much crustal volume, continental crust volume, is being put back into the mantle. My suspicion is that it's not a lot, and that it hasn't been happening for a very long time if there is some down there. The hotspots record little hints of it happening, but I don't think there's a lot of continental crust that's been put back in the mantle. That's my opinion.
Well, see that. So, I mean, it makes sense when you think about how continental crust works, and that it doesn't. It doesn't go down. It doesn't subduct.
Right.
That on early Earth it formed faster, and then it got slower. It's still slowly accreting and getting larger continents.
Yeah.
But they're not. They're just ever growing slowly.
Yes.
But
Slowly.
they're ever
That's
growing,
right.
and they're not recycling back into the mantle like oceanic crust does all the time.
Exactly. The continental growth, the volume or the mass of continental crust is a big open-ended question, and it depends a lot on what you think that recycling rate is, if there's any, and if so, how much continental crust is going back in the mantle today. My opinion is that there's not a lot, and that we've had kind of progressive continental growth through time, which would say that in the future we will have continued growth of continental crust. That's kind of my default view, which not everybody agrees with that at all.
So do we know when most of continental crust formed, like the big cratons, like when they were done forming by? Because I in undergrad and like reading textbooks, you see a lot of like by the end of the Archean, most of like 80% of continental landmass had been created, and then since then it's just been like slow accretion and stuff. But that said, that's still before this like 2.5 billion year number of like potential when plate tectonics began. So
yeah, that's a great question. I was going to go back to the rock ages through time, and if we go back a billion years, then 50%, over 50% of the continental crust has ages older than a billion years. So we know that we, at least a billion years ago, had 50%. At the very least, we had 50% of the current volume.
I was always wondering how that was done. That makes a lot of sense.
Yeah, I mean, that's like the minimum, right?
Yeah.
We go back 3 billion years, and there's maybe 5% of the continental crust has ages that are older than 3 billion years. So, again, we're kind of roughly estimating here, but that's a minimum, because we can look at those rocks and say, 5% of the continents are over 3 billion years old, so therefore they must have been there. So the rest is in model land. And some people would say that, go back 3 billion years and we had 100% of the volume of the continental crust. We had the same volume of continents as we do today.
Really?
Yeah. Again, I'm a little suspicious of those models. I think it's more like 25% of the continents 3 billion years ago or something like that. But these are all geochemical models, basically. In some way, they are geochemical models that people use to go kind of back in time. And it comes back to that recycling versus reworking thing. How much continental crust has been put back in the mantle over time versus how much of it is just recycled, reworked, overprinted, like remelted. Taking a granite at the surface, eroding it into sediments, taking those sediments back into a continental collision zone and melting them to form new granites. That's just reworking. That's the same volume of continental crust just getting reprocessed over and over.
Yeah. So so on that, back to this kind of like, is Earth done differentiating? I am curious because we're not losing, like you said, continents are not losing material to the mantle. They're not being recycled, but they still can be formed, and like partial melting happens all the time at subduction zones, and plate material, oceanic plate material, is being partially melted and turned into more felsic stuff. So is there a potential future of Earth where all like the oceanic crust has differentiated into continental crust and we're just this lid of continent? Or is that not? Is that pseudoscience?
That's a really good question. I've never really thought about it in that way, I guess. I think it depends on your rates. It depends a little bit on when the Earth kind of becomes a dead planet. And dead means heat. The heat inside is getting out easy enough. Like it doesn't. There's no more heat that needs to get out. That's when a planet kind of dies.
Tectonic
stops being dynamic. Yeah, exactly. And so I don't know exactly what the heat loss like curves look like for Earth necessarily projecting that far. Like, could we say, oh yeah, there's continents are growing at some rate and heat is being lost at some rate, and so there's a crossover point when we'll have a lot of continents and heat needs to get out still.
That's
or is
a
it kind
good
of the planet dies before that happens thermally? It's a tough one, but the continents are getting more distilled.
Yeah.
Like and in different ways than they did 2 billion years ago.
Right.
Kind of referred to land plants and weathering cycles on Earth. There's a growing emphasis on focusing on that in the weathering environments change the granite compositions and change how continents are actually distilled and how distilled they are. If you look at the continental crust, like how enriched is the top compared to the bottom? That's distillation, really.
Right.
And so how that happens has changed over Earth history.
Yeah, the differentiation. So it's still happening, and things are still getting more and more, I guess, felsic over time, just slowly. It's
slowly. In felsic felsic. This is in the weeds of granites. It's hard to get more felsic necessarily than a granite, but you can get enriched in other stuff. You can put all the other goodies in there still, just because melting is controlled by major minerals. So it's hard to get more felsic than quartz and two feldspars.
So what happens if granite partially melts? What comes out of that? Just more granite?
Yeah, basically you get more granite. I mean, you get what's called a leucogranite, which has like no biotite in it. The answer is it doesn't really partially melt very much. It's weathering. So you weather the granite, which is kind of a distillation step. Then you melt the sediment again, which gives you a granite that's more enriched in aluminum, for instance. So weathering is kind of a distillation step in the Earth system in a way.
So, and correct me if I'm wrong. I hope I'm interpreting this right. But granites on early Earth and, millions and millions of years ago were more mafic and have become more and more felsic to the point that they're so felsic they can't become any more felsic?
That's kind of right. Yes, the advent, and we don't think of it as mafic and felsic. We think of it as like potassium rich or aluminum rich or not. And so early Earth rocks are very sodium rich, sodic. And those are kind of quote unquote juvenile. Those form at subduction zone type settings on the modern Earth. The potassium rich and aluminum rich granites really start about 2.6, 2.8 billion years ago.
Why?
And those, I think it's because sedimentation started. And you started to continents emerged above sea level at some time. You had a weathering cycle.
Whoa.
And then you form granites from kind of progressive. You could also do it just by progressive distillation. Like if you take the sodium rich granites, granitoid rocks, I should say, from the early Earth and you partially melt those, you're going to get potassium rich granites too. So there's multiple ways to kind of achieve the same goals here. But yes, over time, the continental crust has become more potassium rich, more aluminum rich, at least the upper parts of the crust have.
God, crazy. Okay, really cool.
Yeah.
And you kind of hit on this already. I think you said like 5 or 10%. But the last question was how much granitic, and that, I guess that creates a different question, but how much granitic continental land was exposed by 3 billion years ago?
Great question. So I'm going to say granitic meaning continental crust, like felsic.
Is the answer different if it was just continental land?
Yeah.
Compared to granite? Okay.
Yeah. I would say we have no idea if it's granite specifically.
Okay.
But continental land, well, we don't really know. We know there's some because there's sedimentary sequences that are preserved in the rock record going back to 2.9, 3 billion years ago. We started to get thick packages of sediment, so that you had to have land exposed. Then we don't really know how much, and it depends how much you think continental mass there was. Actually, my view is it's a little bit less. We had smaller and submerged continents before 3 billion years ago, and then after that we started to have larger and more emergent continental crust exposed to the atmosphere, basically above sea level. But
above sea level. Speaking of sea level, this is where we're kind of finishing out this video, but next follow-up video, we will get into when was the first oceans? Was there a global ocean? And did the moon forming impact, was there an ocean before the moon forming impact? And did the moon forming impact completely vaporize it again? So there's a lot of questions surrounding early oceans on Earth, early life on Earth, the moon forming impact, if the moon forming impact played a role in plate tectonics, early tectonics on Earth. So all of those questions will be in our second follow-up because we talk too much and we cannot keep these that short. So
it's
please
impossible to not talk too much with you.
Yes, I know. Well, we get into such great topics. But anyway, we will have a second video hopefully coming out in like a couple weeks max after this one, but we shall see. So make sure to stick around for that. And thank you, Jesse, for coming on.
Oh, thanks, Rachel. It's always a pleasure to talk to you about these topics. You got such great questions on your
Yes,
YouTube
thank you guys
channel.
for
It's
asking
amazing.
these. Oh my God.
So many and so interesting and such deep ones, actually.
Such
It's
deep
great.
ones.
It's
I was
awesome.
really
Yeah.
impressed with all of the
Yeah,
questions.
absolutely.
So thank you guys for those of you who asked questions in the comments. I'm sorry it took us 8 months or whatever to get back.
Yeah, absolutely.